So now we're very happy to have Alex D'Aspremont, who will tell us about regularized nonlinear acceleration.
Okay, thank you very much for the invitation. It's always a pleasure to be back. I should start by saying that this is joint work with Damien Sierre and Francis Bach. And Damien is going to be on the job market next year, so you know what to do. So just a little bit of advertising. We're recruiting non-tenure track junior faculty positions at ENS in data science, whatever that is. And it's a 2-year position with travel funds, competitive salary, etc. So if you're interested in doing good math in Paris for about 2 years, please talk to me during the break. Okay, but today I want to talk about something fairly generic. We're going to focus on the problem of minimizing a function. And what's important in this slide is what is not there. We're not going to make that many assumptions about the function. But it's an unconstrained problem, and that's important here. Otherwise, we're not assuming that the function is convex or anything like that. We will make a certain number of assumptions to get rates. But outside of that, the idea is simply to try to accelerate a generic optimization algorithm, right? So when you do optimization, and you run an optimization algorithm on a problem, and here it's a very simple 2D example, what you get is a sequence of iterates. Okay, it's the quadratic function minimization here using fixed step gradient descent. And once you've run the algorithm for a certain number of iterations, you throw away everything you've computed except for the last point. And that's the standard practice in optimization. So from a statistical point of view, of course, this is a disaster, right? There's a lot of information. We have a sequence of points converging towards a solution, but we're throwing away most of that sequence, except for the last point. So clearly, we can do better than that. And in some cases, like stochastic optimization, algorithms actually keep something else than the last point. They keep an average of the iterates or something like that. But typically in optimization, this is not what people do. You just keep the last point and work on that, okay? So we can do better by exploiting the full sequence of iterates. And the idea is what kind of performance gain can we expect? And can we get bounds, etc. So this is not a new idea, of course, convergence acceleration on sequences. And it dates back at least to Aitken in the 20s. And the Aitken's result is very easy to spell out. So suppose you have a sequence of scalars here with limit s star, and it follows this autoregressive process here. If you have 3 points, 3 iterates, you can get A here. And if you plug in A inside the model, you can get an estimate of s star. Okay? So this is the formula. And that estimate is called Aitken's delta square. And it allows you to estimate the limit s star using only 3 iterates, right? We can do the derivation a little bit differently and assume this linear model between the iterates with a normalization constraint over here. And now, instead of estimating the parameter and plugging it into the model, we simply listed a certain number of linear equations that have to be satisfied by S and the model parameter A and the limit s star. You get this linear system, you solve it, and you recover Aitken's delta square like we did in the previous slide. Okay? That's the same formula as before, but it's a different approach, and it's done using an approach that can be generalized to higher dimensions. So again, the idea, you observe 3 iterates, and using those 3 iterates, you try to estimate the limit. And this seems to work amazingly well. So just a simple numerical example, a sequence here that converges to pi over 4, okay? The partial sums look like this, and after 10 iterations, you get about 1 digit of precision. You apply Aitken's delta square, you use the 3 first iterates, for example, to get an estimate of the solution, and after 3 iterations, you get 1 digit of precision. And if you do the same thing using the last 3 iterates here, you get this estimate here, the delta square, and now you have 4 digits. You haven't computed anything else than this initial sequence of iterates, but you're doing a little bit of post-processing. And this post-processing allows you to get 3 additional digits of precision with essentially no numerical cost.
So just to clarify, in the previous, the assumption that you make is that you're always in the convex hull of the 2 iterates that you mentioned, right? Like the first line that you have here?
This one? No, it's easier to think about it in those terms, so I have an autoregressive model. But here it's not even clear that the model is true, right? So I'm just applying brute force Aitken's delta square to this sequence, and this is the kind of convergence I get. Okay, to make the result particularly striking, I've chosen purposefully an oscillating sequence, and this Aitken delta square turns out to be particularly effective for oscillating sequences. If the sequence was slowly converging towards the solution, I would get less performance. But here, I'm not doing that much more computation, just a little bit of post-processing, and I have 4 digits instead of 1 after 10 iterations. And well, it doesn't stop there. Okay, this is a perfectly respectable sequence of iterates. I can accelerate it as well, and one more time, and get an estimate of the limit, and so on. Okay, that too is an old idea. It's called Wien's epsilon algorithm. It dates back from the 50s. And so there's an entire stream of work on convergence acceleration dating back from numerical analysis in the 60s. It's also, of course, directly related to the Levinson-Durbin procedure, for example, to estimate autoregressive processes. Most of these results are focused on the scalar case, but there are also extensions to the multidimensional case, such as minimal polynomial extrapolation, which I'm going to detail here. Because, of course, in optimization, you're interested in the high-dimensional scenario. Okay? But overall, the idea here is we're looking at a post-processing step. We've run an optimization algorithm, we got iterates, and we want to try to do a little bit of post-processing on these iterates to improve the quality of our estimate of the solution at minimal numerical cost. If the post-processing is more expensive than the algorithm, things start to fall apart. So here, we don't invest too much numerically. Okay, so I'm going to spend a little bit of time recalling what minimal polynomial extrapolation is about, and talk about the regularization version, the regularized version, and get convergence rates. Okay, so to fix IDs, let's look at a quadratic example that you minimize using the basic gradient method. So you're doing fixed step gradient, fixed length gradient steps. And if you write down what's actually happening, you have this vector autoregressive model linking iterates between iterations. Okay? And so we're going to call the matrix of that model A. So k plus 1 minus x star follows a vector autoregressive process. And if we take linear combinations of those iterates and the difference with x star, what we get is a polynomial in the matrix A applied to the vector x0 minus x star. And if I normalize the weights to 1, then I can write that the difference between a C-weighted average of the iterates xi and the limit is equal to some polynomial p of the matrix A times the vector x0 minus x star. And so in particular, if somehow p of A times x0 minus x star is equal to 0, then my C-weighted average of the iterates is exactly the limit x star. Okay, so this is what we want to obtain in the end. So we get the limit by averaging iterates using weights that, of course, depend on those iterates. In practice, it has to be a little bit more complicated than that because, well, we do not observe the matrix A. And so the question is, how do we extract the weights C without observing the matrix A? Well, easy answer. We look at the increments. If you look at the model on increments, this is what iterations look like. And so if P of A is equal to 0, we must have that C-weighted sum of increments has to be 0, 2. That plus the normalizing constraint gives us a linear system that allows us to solve for the optimal weights C. Okay? And so in particular, the polynomial P is the minimal polynomial of the matrix A with respect to x0 minus x star. So you solve a linear system, you get weight C, you average your iterates using those weights, you get an estimate of the solution. Okay? Of course, K can be arbitrarily large, especially in high dimensions. You don't want to solve a very large linear system because that's costly. And so the idea is to do this approximately. And how do you do this approximately? Well, instead of setting this quantity to 0, you minimize it. Okay, and that means solving a quadratic program, again, using these normalization constraints on the increment matrix U. xi plus 1 minus xi. And so you're doing what we were doing in the previous slide, but just approximately. And this is also a classical result. It's known as the Eddy-Messina method, or reduced rank extrapolation with arbitrary k. And it's going to get us an approximate solution to the minimum polynomial extrapolation algorithm I detailed before. Okay, and the question is, how well does this perform? So, of course, we can't really quantify how well this will perform, but there is a very good guess that works uniformly well and involves Chebyshev polynomials. And it's a classic argument, and the idea is this here is exactly equal to this, okay? And again, this can be bounded by something that looks like a condition number times some matrix polynomial times x1 minus x0, okay? Again, this quantity here is smaller than this, where this is the spectral norm of the matrix polynomial P of A. And again, this can be bounded by the max of P of lambda I times the 2 norm of this quantity, and lambda I being an eigenvalue of the matrix A, okay? Typically, we don't know much about the eigenvalues of the matrix A, but we know, at least in many cases, that they're between 0 and sigma, typically when we use gradient descent, for example, okay? And so minimizing this quantity uniformly without any specific knowledge on A is simply solving a Chebyshev problem, right? So we minimize over all polynomials P of degree K, satisfying the normalization constraint, the maximum of these polynomials over the segment 0 sigma. Just the very definition of what Chebyshev polynomials do. And we know that these converge to 0 very, very fast. This is actually the argument behind the convergence rate for Langshaw's iterative methods to compute eigenvalues, accelerating power iterations, for example. So we have very precise bounds on how fast this converges to 0. And in particular, we can show that it converges to 0 with a rate equal to zeta k, where zeta is this quantity here. And if you look at exactly what this quantity means when you're using the gradient descent method on a quadratic function with lower bound mu and upper bound L on the spectrum, the rate you get is this one, okay? So the difference between your estimate of the solution and the actual solution converges linearly to 0 with a rate equal to the accelerated rate, okay? So you get square root of the condition number here instead of the condition number for the traditional linear convergence. So it's important to just pause and understand what's going on here, okay? We are running very naive fixed-step gradient iterations, okay? We get iterates. These are supposed to converge very, very slowly. We get those iterates, compute the weights Ci. We take a Ci-weighted average of those iterates, and now this average will converge with the fast rate. Okay? So we run the very, very naive gradient descent method. We do a little bit of post-processing, and we get the accelerated rate of Nesterov. This is in the quadratic case, and the question is, how can we generalize this to generic optimization problems, of course. Just a few words about something I forgot to say. This too is fairly classical. It's known as Chebyshev, the Chebyshev method, and it dates back at least to Nemirovsky and Polyak, but probably earlier than that. That paper is in Russian, and I couldn't find it, but I know from second-hand knowledge that everything should be there. A reliable source here. And so, so it's a classical technique, and there are interesting connections with classical accelerated methods. There's a link with conjugate gradient. There's a similar flavor, but the key difference here is that we do not observe A, so it's not the same story. What's a little bit more interesting is that, in fact, Chebyshev polynomials satisfy a two-step recurrence. So this is what the recurrence looks like. And you can compare that with the two-step recurrence you run when you run Nesterov's method, and they look very similar, okay? And there are more details in this paper by Moritzhart recently. Okay, so you can look at Nesterov's method as doing a sort of closed form version of the Chebyshev argument I just detailed. Okay, so now the question is, can we do this for generic optimization problems? Well, this is just a noisy version of what we were doing before on quadratics, at least locally, if the function is smooth enough. Okay, so you know a model like this holds in the generic case with some bounds on the Hessian. And now the approximation error in the end is a sum of three terms. The error term we had in the quadratic case, a term which depends on the stability of your estimation procedure on C, okay? And a term which grows with the amount of nonlinearity you have outside of the linear approximation in A, okay? And the key issue here is actually stability. Why? It's easy to see why. If you look at the matrix you're in the linear system you're solving to get the weights, it has a very specific structure. By construction, it's going to look like a Krylov matrix. And that's bad news, because Krylov matrices are inherently poorly conditioned. Okay, so the Krylov problem is directly related to the Hankel or Toeplich's case, and we know that in those cases, the condition number is typically exponentially large. Okay, so that's bad news. And so if you want to do this on nonlinear problems, you need to regularize, okay? In particular, for generic optimization problems, you have noise on top of this. What you observe is actually a noisy version of that matrix, and so there are stability issues at stake. But you can regularize, and it turns out that the simplest possible form of regularization, which is Tikhonov regularization, is enough to remove to solve these stability issues. So instead of solving the original minimization problem, you solve this one with a penalty lambda. And of course, the entire trick here is to calibrate this penalty lambda. And you get optimal weights here. And so this is what the method actually looks like. It's very simple, so why not spell it out completely? You run an optimization algorithm, whatever it is. You get a sequence of iterates. You set a parameter lambda for regularization. You form the matrix of increments. You solve the regularized linear system, you normalize the weight C, and you return the C weighted average of iterates. That's it, okay? And so we'll see how this performs on generic problems. So you can extend what was holding in the quadratic case to this nonlinear scenario, and you get a bound that is slightly more obscure. So instead of having the classical bound, linearly converging bound for Chebyshev polynomials, you get something that is a function of a regularized version of the Chebyshev problem, for which we do not have a closed form solution, but that controls the error, plus terms that depend on the regularization parameter, the condition number, and the amount of nonlinearity. So that's a bit obscure, but it turns out that asymptotically, when you're close enough to the optimum, you can clarify a lot of things by fixing the amount of regularization. And you can show that locally, at least, near the optimum, you recover the accelerated convergence rate, provided you set properly the amount of regularization. And so you get, again, linear convergence for basically extrapolated gradient descent with the accelerated rate. And again, what's going on here is you run the most classical fixed-step gradient descent, the most naive algorithm there is. You keep the iterates, and you take k iterates of this naive method, compute the weight C, average those iterates with the weight C, and now you get an estimate of the solution that satisfies the accelerated rate in Nesterov. Okay?
So what kind of beta and p?
Beta is a scalar parameter that controls regularization, and is there a p somewhere?
That is the norm of p.
Oh, p is the amount of nonlinearity. So
can you set lambda from the data?
in practice, you do a grid search on lambda. So this is just a bound that allows you to control the convergence on paper. In practice, you try a few values of lambda, and you get an optimal list. You check the function value. But I'll show some numerical examples later on. Okay? So the idea is just to get rates, and to get rates, you need the proper of the magnitude for lambda. Okay? So that's deterministic. The question is, can you do the same thing for stochastic optimization? And the answer is yes and no. Otherwise, it would be too simple. So we get a similar result for stochastic optimization that depends on the amount of noise, etc., condition number again. So I'll brush over quickly over this, but there's an inherent conflict in doing averaging for stochastic optimization, okay? When you do acceleration in the deterministic case and there's not too much noise, what we've shown before is that Chebyshev polynomial provide a sort of uniform answer that works quite well and actually gives you optimal bounds. But if you remember what Chebyshev polynomials look like, the weights oscillate very significantly. So they are ill-conditioned, and you're taking averages of iterates with weights that oscillate wildly, okay? When you're doing a stochastic optimization and you have a lot of noise, so in the opposite scenario, you want to do the exact opposite, and you want to compute averages with uniform weights. Okay, so here there's a clear conflict between what you're supposed to do on the deterministic part of the problem, which is average with oscillating weights, and what you're supposed to do on the stochastic part of the problem, which is average with uniform weights, right? And I wish I could say we had solved that conflict, but we haven't. So in practice, what you do here is you set your weights to accelerate the deterministic phase of the algorithm when you're actually working on the signal. And then at some point, it stops working because the noise dominates, and you're essentially producing noise, okay? So that's fine because the interesting phase in the convergence is the first one, but you would want to do something a little bit more adaptive and work on the noise a little bit more, and we don't know how to do that yet. Okay, so we have these two extreme scenarios. When the noise is small, you recover the accelerated rate, but with weights that don't average very well. And when the noise is large, you recover the plain uniform averaging case. And in that case, you're not accelerating very well. Right, so a few numerical results to conclude. So this is what happens when you run this on logistic regression with L2 regularization on the Madelon dataset, etc., something fairly standard. Right? So in gray here is fixed step gradient descent. Orange is Nesterov's method, the plain vanilla one. Green is, purple is Nesterov with backtracking. This is acceleration with using the last 5 iterates. Okay? And this is just the same thing, but with one last line search in the direction given by your estimate of the solution. And this is what you get. So again, it's interesting to think about what's going on here. We're using the iterates produced by this method to get these points, right? So when we're here, for example, we use the last 5 iterates of this algorithm. We computed the weight CI, the CI weighted average of the last 5 iterates. We get to this point. We do line search in this direction, and we get to this point, okay? It's just post-processing. I'm running gradient descent and doing post-processing on the gradient descent iterates.
Sorry, the direction, the line is the one that goes...
The line is the last point you got from your algorithm, okay. The extrapolated one, okay. You do a simple backtracking line search in that direction. Yes?
Could you use as input the iterates of Nesterov?
Yes, excellent question, and it doesn't work. I mean, it works, but basically what happens is that
oscillates, so it should...
Yes, but it doesn't oscillate enough, so you're close, you have more conditioning issues because all your points are closer to the optimum. So you have to regularize more, and if you regularize a lot and you're close enough to the optimum, you lose the benefit of acceleration. So somewhat paradoxically, it's better to optimize a poor method than to optimize a good one. Okay? So, and that's also because our regularization is very crude. I'm sure that if you do something wiser than Tikhonov, you would get better performance on Nesterov. Also, the trick is that Nesterov is a multi-step method, and so you're not exactly in the setting that I described here, because the matrix A is not symmetric, etc. So I could go on and on, but that's the short story. Yes?
So for getting the local accelerated rate, what are the assumptions on the error? Because if the error is too large, maybe it might not allow us to get this fast square root of...
It becomes true when you're close enough to the optimum. And the amount of regularization is proportional to the local nonlinearity. So that's the idea.
So there is like a small limit.
Yes, and it can become arbitrarily small, but it's just to get an idea. It's one way of formalizing the rates. Yes?
Yeah, it's just related to the first question. I mean, Nesterov already has some sort of averaging inside it, so you're doing averaging twice. And also, unlike gradient descent, Nesterov is not always guaranteed to reduce the function.
Sure, but you don't really need a decreasing of the iterates to get the iterates to get acceleration by averaging. So that's fine. But the key issue here, as you said, is basically Nesterov is a multi-step method, and the multi-step means that we are not really in this vector autoregressive framework, at least with A symmetric. And as soon as A is not symmetric, we don't get the accelerated rates. Okay? So it's better to accelerate a slow method. But it turns out that accelerating a slow method still gives you fast rates. So it's enough, in a sense. Okay? Other questions?
Did you compare with Nesterov with restart?
Good idea, with sharpness and so on. We should try, but this is Nesterov with backtracking, so it's the locally adaptive one, but we don't restart yet. And restart works when there is sharpness, so you have to then specify the problem a little bit more. But it's another story. Okay, so let me just finish with the numerical results. So this is the same thing, but with online stochastic gradient, accelerated stochastic gradient, solving again logistic regression. There's a long stream of work, recent work, doing accelerated online stochastic gradient by using variance reduction techniques. And because the variance is being reduced as the algorithm progresses, you can accelerate things a little bit better than in a plain vanilla stochastic case. I won't go into details, but basically, accelerating the basic stochastic gradient gives you a performance like this. And in some cases, accelerating, for example, Saga, which is in gray somewhere, gives you an improvement. But again, the picture is a little bit more mixed. And finally, it's sort of unavoidable these days. We tried it on neural networks. And if you do acceleration on the stochastic gradient method plus momentum, you get this red curve here. And this typically allows you to restart a little bit sooner. And if you restart sooner, you go faster. But there's a very, very long list. So this is one scenario which works. But choosing the right parameters, the right configuration for the algorithm, the right restart frequency, etc., is still more an art than anything else. And so we haven't found a robust strategies to speed up the convergence yet. Okay, so it works sometimes. I can show you an example that works, but I can't guarantee that we have a robust restart strategy, etc., for accelerating neural networks yet. Okay? But here, for example, once you have the proper tuning, you get a speed up of a factor about 2. Okay, so just to conclude, post-processing works. So if you remember one thing from this talk is that when you run an optimization method, it probably makes sense to recover the last few iterates and try to go a little bit further by doing averaging like here, like we did here. Okay, in practice, it means solving a linear system, typically 5 by 5 or 10 by 10, so the numerical investment is absolutely minimal. And if you're lucky, and in many cases, at least in the convex case where things are smooth enough, this will work, you're going to get a much improved estimate of the solution. Okay? So the complexity is completely marginal, so it makes sense to try it no matter what. And again, in practice, we do get a convergence speed up over optimal methods, even the adaptive ones. Okay? And it's adaptive. It doesn't need any knowledge of the smoothness parameters. I'm not using any information about the strong convexity or the Lipschitz constant of my gradient. Okay, that's a feature. It's also a bug. Maybe I should be using this information if I have it, or if I have estimates of the strong convexity constant mu and L. But because the regularization I'm doing here is very naive, I'm not accounting for this additional structure of the problem, and that should probably improve things a little bit. But we need some different kind of regularization, and so there's still a lot of stuff to do. Maybe we might be able to extrapolate accelerated methods if we can solve the stability issues. We need to work on constraint problems. So adding a convex constraint shouldn't be that hard. The problem remains convex. but it's going to increase its complexity significantly because now you have an extra feasibility constraint on the linear system you solve to get the extrapolation weights, and it's not clear at all that extrapolation remains very, very cheap. Okay, so that's going to depend on problem structure, but it might work otherwise. And we should handle smooth functions a little bit better. So just to finish with a short list of open problems. So again, we should regularize in a more structured way. Okay, we are estimating the limit of a vector regressive sequence with a fixed point. We should account for that in the way we regularize. We don't do it yet. We have information on the spectrum of the model matrix A. We don't use it when computing C. We should. It should help. And also, there is this strange regularized Chebyshev problem. We can solve it using sum of squares, okay? But we don't have explicit bounds on its convergence as a function of alpha. And if we want to improve the results on stochastic optimization, we need to better understand the impact of regularization on the convergence of these bounds. But I'm not sure yet how to get bounds on a problem like this, outside of just solving it using SDPs. Okay, so that's it for today. Thank you.
So, quick question. So, you use only your 5 last iterates in your.
Yes.
So you could presumably keep also your gradients. Do you think this could actually improve the post-processing by actually using this information?
Good idea. I haven't tried, but. Because it's simple gradient descent in a sense, it's fixed step gradient descent. So the gradients are implicitly inside the iterates up to a linear transform. But if you use wiser methods, suddenly this link is not clear anymore. So I guess you might be able to do something. And it may have to do with a more structured way of regularizing the weights estimation problem.
Okay, let's thank Alex.
Yep, thank you.